Welcome back. Let's start our second talk. Our speaker is Prakash Saivasan. He works in theoretical computer science in IMSc.
Yeah, today we will look at something called logic and computability, which has relatively close connections to math, so I hope I don't disappoint anyone if you have some expectations. But in general, the story would be like this. We will first start with, things about infinity, which most of you would know. And hopefully it is new to some of the BSc students. Then we will, in particular, we will look at Cantor's theorem, which says that power set of a set has a cardinality strictly greater than the cardinality of that set. And then we will see how it is useful in the theory of computability. So the theory of computability asks whether there is an algorithm or a program that can actually solve things. And if you want to distinguish between a problem that cannot be solved using a program and some problems that can be solved, essentially the Cantor's diagonalization trick will play a crucial role. And in the last part, there are three parts. In the last part, we will actually look at some applications of this computability in logic. And this is probably the most interesting for most of the mathematicians here. Go into the talk. And so the initial part, as I said, will be some interesting aspects of infinity. I will follow something called, let's look at it as a story, and the story will be about something called Hilbert's Hotel. Yeah. So the Hilbert's Hotel, this Hilbert's Hotel problem was introduced in 1924 by Hilbert himself to explain infinity, and we will try to follow the same pattern in some sense. Here we have one room for each positive natural number, and then we want to check whether we can accommodate many people into it. So essentially we have infinite set of rooms, hotel rooms. There are our friends. This is the hotel manager and his wife. His wife apparently is also a mathematician. So we'll see how she assists the manager. And so there are, each of these rooms are currently occupied by positive numbers, and there are infinitely many of them. And in one rainy night, 0 comes. So the manager, of course, is very happy. He's getting a lot of money. And one night, 0 comes along and asks whether there is a room. Now, the manager is confused. He said, but all my rooms are actually full, so I probably cannot accommodate you. But let me ask my wife. Maybe she has a trick. So he goes and calls his wife. The wife immediately says, oh, this is not a problem. Just shift all of them. You should already know it, right? So you shift all of them by 1. And then now she finds a way to accommodate 0. And the manager is quite happy because he has extra money now. Yeah, so she accommodates 0 by shifting each number to next position. But the next day what happens is, so what we know from here is that cardinality of natural numbers, assuming 0 is not part of natural numbers, is same as natural numbers union the set 0. So you can always accommodate 1. You can also accommodate finitely many sets, and still the cardinality does not change. So the next day, all the negative numbers also come. And then they say that, can you please provide us accommodation as well? Now the manager says, oh, but already yesterday we provided an accommodation for 0 and we are full. But still, let me ask my wife if she can help. She comes immediately and says, yes. So she says, okay, accommodate all the positive numbers in the even positions. And then now we have positions for each of the negative numbers. And she tries to accommodate all of the positive and negative numbers in the same hotel. And manager is very happy. So he says, okay, fantastic. Then the next day, set of all rational numbers came and asked, can you accommodate me as well? Now the manager is a bit confused. We already have the hotel full now. How do we accommodate all the natural numbers? In fact, he actually rightly kind of observed that everybody staying in the hotel is already part of your bus. So, I mean, he does not know whether this number is too big to be accommodated in the set of hotels that he has or not. But he nevertheless, he thought he will go and ask his mathematician wife. So the mathematician wife was out of town. So we'll help the manager solve this problem. So of course, there are pairing functions. You could directly try to find a bijection between rational numbers and natural numbers, but we already have a injection from n to the rational numbers, like our manager rightly observed. Can we use this injection in some sense? In fact, we can also give an injection from rational numbers to natural numbers. So how do we do this? So we all know that every natural number has a binary equivalent. Do you agree with me here? And every binary number is actually a binary string. Do you also agree with me here? But can every binary number be transformed into a binary string, be transformed into a binary number? Can you give an injection from every binary string? So here a binary string is any word that contains 0 and 1. Exactly. So just append a 1 behind it, then you get a binary number. For instance, if you have a string 0, 0, then you can transform it into a binary number by just appending 1. So you take any binary string, append a 1, you actually get a binary number out of it. So what do you know from here? You know that number of binary numbers is exactly equal to the number of binary strings. Okay? In fact, this also gives us an injection from set of all n cross n to the strings. You give me n comma m, I'll just transform it into 0 power n, 1, 0 power m. So you get a injection from n cross m to binary strings. Do you agree with me here? Did I lose you already? Or? Okay, very good. Okay, but now we do have an injection from natural number to rational, and yeah, this tells us that number of n cross n is exactly equal to the cardinality of the natural numbers. We have an injection from rational numbers to n cross n and hence to n, and we also have an injection from n to rational numbers, but we need a bijection. So here is where theorem comes into picture. This theorem is called Cantor-Schroeder-Bernstein theorem. So what it says is, you give me two injections. So if you have two sets A and B, and you have an injection from A to B and an injection from B to A, then actually there is a bijection. It's a very strong, powerful statement. We'll try to not prove it completely, but at least give a proof idea of why this is true. Okay, so this theorem says that if there is an injection from A to B and injection from B to A, then there is actually a bijection. So to see this, somebody had a doubt or no? Okay. Yeah, so this also says that if you have two sets such that cardinality of one set is less than or equal to the other, and the other cardinality of the other less than or equal to this set A, then the cardinalities are equal. So let us try to arrange all the elements of A in a line. It's not any real line, it's just arranging all the elements in a line. Similarly, we'll arrange all the elements of P in a line. Now we know that we are given that there is a 1-1 function from, we have an injection from B to A. So you look at all the elements. You look at all the elements. Yeah, so this injection actually gives a subset of A to which it maps, right? Now this, if you just restrict your A to G of P, then this is actually a bijection. Do you agree with me here? From this G is a bijection from B to this G of P. So if it actually covers whole of A, then we already have a bijection. But if not, then there is actually a part which is left out. Let's call this C0. Now, of course, this G is, remember that it is a bijection from B to A minus C0. And there is this C0 which is actually left out. And if you remember, our idea was, or our aim was to give a bijection from A to B. Now, we need, am I audible still? Okay. Yeah, so what we do is, now we try to partition this A into two sets. So we look at where this C0 takes us. It takes us to some D0 using this F. And then we look at where this D0 takes us through G. Let us call this C1. And we keep doing this. This gives us a partition of A into some set C, which is this union of all the C0, C1, C2, and so on, and rest of the elements. What you know is from rest of the elements, of course, G is defined, or G inverse is defined. Do you agree with me here? So we have left out the C0 part. So for every other element, G inverse is defined. And in fact, you can also see that this C0, this F is a bijection from C0 to D0, G is a bijection from D0 to C1, and F is again a bijection from C0 to D1, and so on. So in fact, using this, we can actually give a bijection which just takes any X out of this C's and maps it using a F. And for all other elements, it just gives a G inverse of X. So of course, you need to show that this is actually a bijection, but this I leave it as an exercise for you. Okay, so now we have given, now we know that the size of natural numbers and size of rationals is actually equal, and we have a bijection. So both manager and his wife, they are happy. So in fact, you can also show that countably many, union of countably many countable sets is also just countable. So since you have countably many sets, you can index them by natural numbers. And then each set you can arrange according to some natural order. And this already gives you a mapping from each of these elements to n cross n, you see. So the indices of Si is I, 1, which is of the form some natural number, natural number. And this already gives us a injective mapping. And it is easy to see that the size of union of countably many countable sets is actually only countable. So here I would like to say that here we implicitly use some axiom called axiom of choice. This will come to later. I mean, this will be useful, or we will reference this at a later point. So at least remember that we had this proof, and I mentioned that, remember that I mentioned that we use something called axiom of choice here. Yeah, so now the question is, do we have any other infinity other than countable at all? Well, it happens that no. I mean, if you take power set of natural numbers, it has cardinality strictly greater than cardinality of natural numbers. So what is the proof? So assume that cardinality of natural number is same as the cardinality of the power set of natural numbers. Then you have bijection between the set of natural numbers and power set of natural numbers. Let us call it F. Now consider this set S, which is set of all x such that x does not belong to f of x. So f of x, remember, is a bijection from n to power set of n. So this f of x is actually a set. You collect all the elements that do not belong to f of x. Now, since we have a bijection, this S set is mapped to some n. Now, for that n, this n belongs to S if and only if n does not belong to S. So we get a contradiction in this form. So there is also a nicer way to, or maybe not a nicer way, alternate way to look at this. you can look at it as a diagonal. So you can arrange all your elements of n in on the top of the table, and all the sets as a column of the table. And here you can identify each set by an infinite string of 0 and 1. So 0 means that 1 does not belong to f of 1. Here 1, for instance, the first row, 2 belongs to f of 1, so we put a 1 in that particular place. 3 does not belong to f of 1, so we put a 0 there. 4 belongs to f of 1, so so we create such a table, and what our Cantor's theorem essentially is doing is it is taking this diagonal and flipping the elements. So there are, since this P of n has strictly greater element, or it has more elements than size of cardinality of natural numbers, it is essentially trying to construct a set which does not belong to any of the f of 1, f of 2, f of 3 that you assumed is just countable. Okay, so this is all about the preliminary part about infinity. So now we will see how this theorem actually is useful in computability. So the computability asks whether a particular problem can be solved using algorithms or programs. So you give me a problem. Is there a program that can solve this problem or not? So let us look at one of the problems. I mean, you all know programs, right? All of you have looked at some form of programming, I assume. So there is, let's say, I ask whether you give me any program, can I check whether that program terminates or not, program halts or not? Okay? This is a problem, and then you want to write a program for this. So this is this halting problem. So can I check whether a program halts or not is called the halting problem. So this was, as an example, suppose I give you this program and ask you whether it halts or not. What would be your answer? It halts. Okay, yes, it does. But suppose I give you a very complicated program. I will not ask you this question because I do not know the answer myself. But then Turing solved this. He said that there can be no program that essentially solves the halting problem. So we'll try to look at the proof of it. It is devilishly close to Cantor's proof. This we will see. So suppose we had, let's assume for the sake of contradiction, suppose we had such a program that solves the halting problem. That is, it takes a program and data and then outputs whether it loops or not. So it correctly outputs whether it loops or not. Then what we'll do is, we'll construct another program on which H fails. So we will come up with the contradiction. It is very similar to the Cantor's proof that we saw. So how will we construct this n? The program n. So it will take a program. It will not take program and data, but it will just take the program. And if you all agree, you can look at program file as a data itself. It is just some sequence of numbers. You can think of it as a data. Now what it does is, it considers program itself as the data. So program plus program itself as the data, and then it provides it to the program H that you promised me. Program H, remember, is the program that you said will solve the halting problem for me. Okay? Now what this crazy guy does is, he will loop if the program H says the program halts, and he will halt if the program H says the program loops. So the program H always halts and tells you the correct answer. So even if the program H, looking at the program, will tell you whether it halts or not. And based on this, the decision of program H program n will do just the opposite. So you immediately get a contradiction here. So for instance, the program n will halt if and only if program h says n plus n loops, right? So let us look at this with respect to this diagonalization, what is happening. So essentially, what program h essentially promised us was that it can create such a table, and it can actually output the values of such a table deterministically. That is, if you give me some P1 and data as P1, it tells you whether it loops or halts. And what this program n did was, it went through this diagonal and flipped the diagonal. So if program h told me P1 halts on P1, then the program actually tried to loop, it halted. And if it said it halted, so for instance, if program h told me P2 halts on P2, then the program n looped. So essentially, it tried to flip the diagonal. So here, I would like to point out one thing, that it is again Cantor's. It is very similar to Cantor, but at the heart of it is there are uncountably many program behaviors, and there are only countably many programs. So program is some finite object, right? It is written as a finite number of instructions, and it is a finite entity. So you can only have countably many programs, whereas the behaviors of programs is uncountable. So you cannot have, the proof here is trying to pick out a behavior that is not captured by any of the program. Okay, here I would like to introduce not halting problem. So we will need this for our next part. This is our second part, remember. So we had, first we talked about infinity. I don't know if I'm going too fast, but. So we will characterize what we will need this not halting problem, and we will try to see some properties about this not halting problem. So you give me a set. I say that set is recursive if there is a program, terminating program, that can check whether an element is present in it or not. So it can actually determine the membership of a particular element in that set in some sense. Now we say it is recursively enumerable if there is a program that can check whether the element is present, but it need not terminate if the element is not present. So essentially it can, if you give me an element, it can check whether that particular element is present. If it is present, it tells you the correct answer. And if it is not present, there are no guarantees. It can either say no, it can just go into a loop. Now, of course, we consider this halting problem that we saw as a set. So it is set of all programs P that halt on input X. So you can consider this halting problem as a set. And it is easy to see that this halting problem is actually recursively enumerable. So you just simulate P on X, and if it halts, you tell it halts, but it might never halt, so it does not matter. If it does not halt, it does not matter. So this HP, this set HP is actually recursively enumerable. And we also saw that this HP is not recursive. This we saw. So if two sets, so if a set and its complement is recursively enumerable, then then that set is actually a recursive set. Anybody know why, or can you try to find out why, or reason? Exactly. So you run the program that corresponds to S or its complement. One of it will fetch the answer, and then you can actually give out the answer. You can create another program that runs both of them parallelly. One of them is ensured to give you an answer, so the set itself will be recursive. Now, since HP is recursive but not recursively enumerable but not recursive, the complement of HP is not even recursively enumerable. I hope this is clear. So we will use this part crucially in our next part. So we know that HP is recursively enumerable because it's halting problem. You can just given a program and X, you can simulate that program and tell whether it halts or not. And it is not recursive because we saw that there is no program that can actually take a program and input and tell whether it halts or not. So we know that the complement of HP is not even recursively enumerable. So recursive, a set is recursive. We say a set is recursive if you can deterministically, you can determine the membership in that set. If there is a program that can determine the membership in the set. Recursively enumerable is, you can determine here recursive is one that determines both its presence and not presence. So there is a program which will tell you whether it is present or it is not present. Whereas recursively enumerable, it is enough if there is a program which actually tells if it is present. If it is not present, it can do anything. It doesn't need to halt, for instance. For instance, halting problem, right? So we said that halting problem is a set. For instance, you can give a program and the data and ask whether there is a program which actually halts on X, for instance. Okay, so the last part of the talk will be application of these methods that we saw to logic. So in particular, we will try to see a proof for Gödel's incompleteness theorem. So what is Gödel's incompleteness theorem? It says that there is no proof system for number theory which is sound and complete. So what does this mean? It says that you cannot hope to prove all theorems of number theory. This is what Gödel's incompleteness says. Well, this is a very powerful, it's a really powerful statement to make if you. So what is a proof system? So it is some set of axioms and set of proof rules. So what is a proof essentially? It is you either write down an axiom or you can derive some statement based on whatever you have written before. So this is a proof, and a proof is a finite entity, right? So what is sound proof system? Sound proof system is one which only proves true statement. It is useless if it also can prove false statements, right? You want to only prove theorems in some sense. And complete proof system is the one that can prove all theorems, essentially. Unfortunately, Gödel proved that there is no such complete and sound proof system for number theory. In fact, if it is not sound, then you can prove a false statement, and then you can prove everything. So essentially, you cannot have a proof system that is both sound and complete.
If I don't have a proof of a statement, then how do I know it's true or false?
You cannot know.
How this statement?
So we'll come to this. So for instance, you have this axiom of choice that I said, right? So we do not know whether, so there is something called ZFC. You've heard of this. Have you heard of this, ZFC? ZFC is a set of set theoretic axioms that you can use to prove various other statements. There is also a set of axioms which does not include axiom of choice. So Paul Cohen actually proved that you can neither prove or disprove this statement, that axiom of choice can be derived from just the ZF axioms. Okay, or there is also, essentially this theorem is just not something in air. There are, for instance, there's something called continuum hypothesis, which asks whether is there a set which is strictly greater than the cardinality of natural numbers and strictly less than the cardinality of the power set of natural numbers. Now, Paul Cohen again used some technique called forcing and said that this statement cannot be proved or disproved in ZFC, for instance. So we will never know, at least till we change our proof system, we will never know whether continuum hypothesis is true or not. Is this okay? Yes, so essentially yes. So, for instance, the examples that I gave. So we said that axiom of choice cannot be proved in a particular proof system, ZF. This is what we know. So what the example that I gave was that the axiom of choice cannot be proved using ZF. So ZF is a particular proof system, and in that proof system we cannot prove axiom of choice. There could be another proof system where you could prove it, but that proof system also will be incomplete. There will be other statements which are outside its purview. This is a Fields Medal winning proof. Yes, this is a very profound theorem that was proved by Paul Cohen, which actually fetched him the Fields Medal. Somebody else had a doubt, or? It is an open problem to find a proof system, yes, where it can be proved. But even if you find such a proof system, there will be theorems outside it, which it cannot prove. So for instance, you could just, for instance, you can very easily prove by making it an axiom. And if you keep adding axioms to your proof system, at some point it can actually become inconsistent. So it can start proving both true and false. So you cannot just say, I can keep collecting axioms. And if you fix a particular proof system, there are theorems out of it. Maybe offline. I don't have it up. Yeah, for instance, your piano's axiom are some examples of axiom, but I don't know. I do not want to say something wrong. But okay, I'm not very sure of this. Okay, so now we want to prove this theorem, which says that any proof system, for any proof system, there are theorems outside it which cannot be proved in some sense. So at the heart of this proof will also be Cantor again. So again, at the heart of it, if you see, there are uncountably many theorems in number theory, whereas any proof is just a finite object, right? So there can only be countably many proofs. So this will be at the heart of the proof that we will see, though it is not so evident from the proof that we will see now. But if you go back to Gödel's original proof, this is at the heart of the proof of this theorem. The theorem is this, that we are going to prove that number theory has no sound and complete proof system. This is what we are trying to do. A true statement is, it is theorem, for instance. It just depends on the axiom, and based on the axiom, it is true. It is always true on all models. On all models for that particular axiom. For instance, if you take Peano's arithmetic, any theorem is actually true of all natural numbers. So no matter which model you give, it is true of all the models for the Peano's axioms. So it is a true statement, as in the formula or the logic will always evaluate to true no matter what the structure is.
Basically, soundness means if you have statements and it has a proof, the axioms are not inconsistent.
No. So we'll assume that axioms are consistent, as axioms are true statement. And if you actually give me a proof, then if I derive something out of that proof system, which includes the axiom and set of proof rules, then I only derive true statements or theorems. So I don't so essentially what it says is that, so you can write down your axiom, then you can write down some derivation based on the axioms, and whatever you derived is actually a theorem. It is not a false statement. Completeness says that you give me any theorem of that particular, for instance, if you take number theory, you give me any theorem in number theory, I should be able to prove it using my proof system. Set of axioms and the proof rules that you use in that particular proof system. So is this okay? True statement.
And true statement is not something you can derive using axioms and proofs. Because this theorem says that not all true statements are derivable.
Yes. So you have this structure of number theory. So you have this natural numbers, you have this plus, dot, division, multiplication, and so on. So this is a structure, and any statement that you can make on this particular structure, okay, there are infinitely many primes. This is a theorem. So there are infinitely many primes in this structure. This is natural number, plus, minus, addition, and so on. This is a theorem of this particular structure. So, but we will. Yes, this is a. Yes, I mean you don't call it a theorem unless you have a proof. But what I'm saying is, there are statements which are true, for which there are no proofs. This is what I'm saying by incompleteness. So, pardon? Okay, I'm not saying that I'm going to list out for you all the theorems that don't have proof. I'm saying that there exist some statements which are actually true, but can never be proved in any of the proof system. This is what I'm saying. So this is not a constructive way of saying that I will construct for you a statement that is true, but that does not have a proof. I mean, it is also possible. For instance, I told you that this continuum hypothesis is one such statement for which it can neither be proved nor be disproved from within a particular proof system. Is this okay? I mean, yeah. See, if you take any statement, either that statement is true or its negation is true, correct? So one of them is guaranteed to be a theorem. So there are particular statements for which you cannot find out whether one of it is actually a theorem. So you do not know whether continuum hypothesis is true or not of continuum hypothesis is true. Is this okay?
So there exists a statement for which you can prove neither itself
nor its negation, yeah, essentially. So are there any other questions? Yeah.
So there may be statements which are always hidden.
I mean, yes, essentially there are many statements which we don't even know that they are.
Because of our lack of understanding, but because it is always hidden, we couldn't think of any system which can construct to that particular statement, which can lead us to that particular statement. If we cannot have a proof system, which could prove a particular statement, which is always beyond the particular proof system, then we couldn't logically get to that particular statement.
Yes, there could be hidden. I mean, even there are true statements for which there are proofs that are also hidden. Unless they are interesting, you don't go behind them. No, this is also. I mean, both ways are true. There could be theorems for which which could have no proofs. There could be theorems for which there are proofs and they are still hidden from us in some sense. Any other questions? Okay, let's continue. So before we delve into the proof, we'll somehow fix the definition of a program. So we will make it formal. I mean, program is too general a model to work with. So what we'll say a program is it has a finite component and it can write to memory cells. These memory cells are essentially infinite. This has a name. It is called Turing machine, but we'll not use we'll just still call them programs here. So essentially, this is not very unreasonable to assume that a program is of this form, because if you look at what happens in your computer, you compile a program, it becomes a binary, and then what this binary does, this executable, whatever you call it, does is just goes and manipulates the memory, right? This is all a program does. It goes and writes to a particular memory location, it changes a particular memory location, it goes to another location, writes something else, and so on. So this is what a program in your computer does. So it is not very unreasonable to assume the definition of program to be some finite component and which can manipulate memory. So this will be our definition of the program. Is this okay? So we'll also further assume that in each step, this program can go to a new state, it can modify the current memory location, and it can either go left or it can go right. Okay, this is what our program can do. So it has some memory cells, and this guy is having a head pointer which actually looks at a particular memory cell. He is having a position in his memory cell, and in an instruction, he can change his state, he can modify the memory location, and he can either go left or he can go right. This is all a program can do. This is the model, or this is the definition of program that we will work with. Is this okay? Is this part okay to all of you? Yeah, so now we have changed the definition of program. So this program still has all the bad properties that our original program had. So the halting problem is undecidable here, even with this modified definition. So how do you describe at any point a program has a head component, it has something in the tape, and it has a state. So we want to capture this information as a finite entity at any point. So it has certain memory locations that it has seen. We will also include some blanks, but we will only cut off this memory cells to a finite point and only keep that as our configuration. We will also record the state that it is in, and we will also record the pointer where the memory location is. So these are the relevant information to continue your execution of program. This we will call as the configuration of a program. Okay. If you have questions, you should ask me now. Okay. So we will represent this slightly differently. We'll just encode. So we had this head component and state component. So we will just place it in the cell where we'll place the state in the cell where the head is pointing to. So this is an easy way to represent it. This is a finite number of memory cells that we are recording. We don't need the infinite because, we are not going to look at all the memory cells during a single execution. We can increase these memory cells as required if we want to. Okay. Now I call the computation as sequence of related configurations. So we know that that is a configuration of your program. The second row is also a configuration of a program. If those two are, if the second one is got from the first one by a transition of your program. So remember the transition is, it can either change a state, it can do some modification to the memory cell, and it can go in a particular direction. For instance, if your transition was change state Q to Q dash, replace C by A and go right, then the second configuration is what you got. Let me try this once again. It works now. So here, this is the first configuration. Using this transition, you change this C to A, and your head moved from this cell to this cell. So the resulting state, you record it in the second cell. Okay? So these two configurations are related by a transition, and this is a sequence of configurations, each of adjacent where adjacent configurations are related by a transition. Okay? Now, when is a program halting? The program now in our definition. So I claim that if you have a sequence of configuration that starts from the initial state, ends in a final state, okay, we have something called a final state, and as soon as our definition now changes, we say that it is halting if it goes to that final state. For every other state, let us say it just keeps doing some random operation, okay? So if it can, so now the halting problem reduces to whether there is a sequence of configurations that starts from initial configuration, ends in final configuration, and where two adjacent configurations are related by a transition. So this is what is a witness to our halting problem. Do you agree with me here? So this is what I said. So there is a sequence of configuration that starts from the initial configuration, ends in a final configuration, and where adjacent configurations are related by a transition in the program. Okay, this forms a witness for our halting computation. If you can find such a sequence of configuration, then we know that the program is halting. Do you agree with me here? Any questions here? Okay, now that we have some information of what a halting computation is more formally, let me try to tell you the proof idea of the statement that I made, the Gödel's incompleteness statement that I made. So the proof idea is, firstly we observe that if there is a sound and complete proof system for number theory, then I can write a program that, given a theorem, can identify a proof for it. So what is actually a proof? It is a sequence of finite statements, which is either an axiom or each statement is derived from some previous statement using some proof rules. So assuming that if number theory has a proof system, which is sound and complete, I will search for a proof. I will just go through all the proofs in some lexicographic order, for instance. And then as soon as I find a particular, either the statement or its negation is true, so I search for whether the statement is true or negation is true. If the negation is true, then I say that this is not a theorem. If I actually find a proof for this particular statement, then I say that this particular statement is actually a theorem. Okay, is this okay? Let's assume that it is finite. It can be recursively enumerable, but I mean, we are not talking about any particular proof system.
If you're counting it as for all natural numbers, then does it count as a statement for every single n, or is it all?
Yes, but for all natural numbers, is actually a statement, right? For all x, x is, yeah, for all x, x is greater than y is a statement of, this is a particular statement. So it says that, okay, let's say for all x there exists a y such that, or there, okay, for all x there exists a y such that y is greater than x. For instance, this is a true statement in number theory. So if there is a sound and complete proof system, now this proof system tells you certain axioms and it also tells you some proof rules. Now you keep applying these proof axioms and proof rules and see whether you can prove this statement. You can eventually come to this statement. If you can come to that statement, then that is the proof for the statement. May not be the most elegant proof, but it is certainly a proof for the statement. And that is, then you say that, okay, this is a theorem. Or you can either come to this or you can come to its negation. One of them is true, and you can accordingly say whether it is a theorem or not, for instance. This was your question, right?
Again, the proof for this statement would start with one of the initial states would be one of the axioms, and then you follow the proof rules.
Yes.
You will end up with the last statement. The final state would be the state.
The statement, yes, yeah, yes. Or the statement could itself be an axiom, in which case you just write down that axiom. Okay, so what we already know is that this HP complement is not even recursively enumerable, right? This we already know. Suppose I can give you a formula psi of m of x such that not of psi of m of x is true if and only if mx belongs to HP complement. Then what do I have? HP complement is not even recursively enumerable. So I will come back to this slide. So we know that so we know that there are a set of true statements that are not even recursively enumerable because we have one for each entry in our knot of HP, right? So what we said here was, how do I go? So we said that for each member in HP bar, we have a particular statement that is a theorem. And we know that this guy is not even recursively enumerable. So set of all theorems is not recursively enumerable. And we said that if there was a sound and complete proof system for number theory, then I have then this set of all theorems is recursively enumerable. Now the proof would show that we cannot have a proof system that can prove all theorems in number theory. So I hope the proof idea is clear to all of you. Okay, maybe P comma X, maybe my notation is wrong. So M is for programs. So your HP bar was set of all programs comma input such that the program does not halt on this input X, if you remember. Do you agree with me here? So HP, we defined it as set of all programs comma input such that HP we defined it as set of all programs comma input such that the program halts on this particular input. And HP bar is set of all programs comma input such that it does not halt. So yeah, this M should be P in the notation that I followed. Did I lose all of you or some questions is welcome? This is something that we will show, yes. Not this, but I will show something. I will show this, that for each m of x, we will construct a formula psi of m of x that is satisfiable if and only if there is actually a witness for this halting computation. Then if I construct this formula, then not of this formula is what tells you that there is no halting computation. Satisfiable means there is a witness for that M halts on X. You can think of it as a proof, but that is a. Yes, this will be a statement in number theory. So there is a number that you can assign to each of the, if there exists X, then you can actually assign a number to that there exists X. If it is for all X, then it should be true for all the numbers in natural numbers, and then ultimately the statement has to be true or false. Yeah, questions are welcome, so that I know that you are following, or did I lose all of you? Satisfiability means that there is, so I can give, so I have a formula, and it is true for, suppose, for instance, if I say, what was that? For all X there exists Y, X is less than Y, okay? Then actually I can provide a valuation for X. No, I can provide a valuation for Y, so I fix a number, there is for all X. So I fix a number for X, and for each of this number, actually, I can provide a valuation for Y such that X is less than Y. For instance, 5 is less than 6. So, and you just take n and n plus 1, for instance. So this n and n plus 1 is actually a satisfiable assignment for this particular formula. It just says that there is evidence that for particular structures, this is true. It need not be true for all possible structures, but it is true for particular structure. M is the program. If you remember, M, comma X, it should have not been an M, but it should be P. So your HP complement contains program and input such that the program does not halt on that input X. This particular is not a halting problem instance, yes. And this HP contains set of all such not halting instances. So, no. So can you repeat your question? Yes, but you see there is no proof for not halting. What is a proof for not halting? I mean, for halting, of course, I can find a proof. If it halts, then there is a proof. But for not halting, there is no proof, right? I mean, how do you prove that a machine on X is not halting? So if a machine X halts, then I can actually simulate it and say that, okay, see, this is the sequence of statements that it followed, and after a particular amount of time, it actually went to the final state. Whereas, what is the proof for not halting? There is, I mean, you get the point, right? Somebody else had a question? Okay. Now that we have this proof idea in place, so what is a halting computation? Let us come back to this slide. So we said that it is sequence of configurations that starts in initial state, ends in final state, and adjacent configurations are related by a transition. This is somehow the witness for to the fact that a particular P comma X is actually a halting computation. Do you agree with me here? This is what we said. But we want to somehow build a formula that works on numbers. So we want to represent this witness as a formula, I'm using first order formula very bit carelessly without defining it, but I'm assuming that all of you have seen some form of first order formula in your mathematics before. So how do you represent this as a number and then a formula that is true of only these halting computations? Okay, this is the problem, right? So what I will do is, I'll assume that each memory cell, so your configuration is some memory cell with some either value or value comma q, right? This is what we said each memory cell contains in my configuration. I will encode it as a prime number, some PRE. I will encode the configuration as a PRE number where P is some prime. Now the question, the witness, halting witness, now reduces to, is there a PRE number of length d such that it can be partitioned into some C-sized segments such that the first segment it represents the initial configuration. The last segment represents a final configuration. And every intermediate segment is actually related by a transition. So what I'm trying to do is take this configuration. I can always interpret it as a number, right? So I can get a very big number, and I can check whether there is such a number which actually witnesses a halting computation. Is this okay? Questions? I don't have a question. Okay. Okay. Yeah, so essentially now we want to come up with a formula that somehow witnesses this particular number, a number that is of length t that can be partitioned into some C length digits, and the first sequence of digits is actually a representation for the initial configuration. The last C digits is a representation for the final configuration, and any adjacent C length number in this big number is related by a transition of our program. Okay, so we fix our program p comma x and then write down a formula for that particular p comma x. Okay. Okay. So we want to construct a formula that is somehow that can witness this number, such a number, that can actually form a witness for such a number. This is what we want to do. So the components of the formula that we will construct will have an initial part, a final part, and the consistent part. So these are the three things that we need to check, right? That the C length sequence, the first C length sequence in this number is the initial part. The last C length sequence is the final part, and that every adjacent C length sequence is actually related by a transition. Do you agree with me here? So one useful statement, number theory statement that will aid us is how to pinpoint a particular position in a large PRE number. Okay, assume that you give me a y which is a power of p, then I tell you this formula is true only if there is a b in v at position y. So this formula ensures that there is a b in v at position y. I'll explain this formula to you in English. So what it says is, so v can be decomposed as some a which is less than y, and remember that b is a power of p. So there is a which is less than y. There is a b at position y. So y is actually a power of p. So at position, the power of y, at that position there is a b, and it has something more after that, and anything more after that is actually greater than py. So you essentially you have this number. You want to check whether at particular position, this particular position, there is a b. So you decompose it as the number that is shorter than this position and number that is greater than this position, and then v can be represented as sum of these three numbers. This is what this formula is stating. Is this okay? So what are we wanting? We are wanting that we have a formula which takes a number v and checks whether there is a b at position y. Okay, this is what we want. So this is an auxiliary formula that I will use to construct my main formula. And how do I construct this formula? I say that I can decompose v into three parts. One that is below the position of y, one that is above the position of y, and at position of y I have by. Is this okay? So in this way I have a handle to, if you give me a y, I can check whether at that position y, p exists or not. Is this okay? Doubts? No? Is this okay? So either it is okay or all of you are lost. So one of these two things. Okay, so here I assumed y to be power of p. So I also claim that I can have a formula which actually checks whether y is indeed a power of p. This is another formula that I will use. What does this say? It only says that the only prime decomposition for that particular y is p. This is all it says. Is this okay? So for all primes, if you can decompose y into some prime and something else, then that prime better be p. So there is only one decomposition, one prime decomposition for y. Is this okay? So what do I have to check that a configuration is actually initial configuration? So for initial configuration, you have the input written there, right? You have p comma x, and you essentially have to start with a configuration starting from x, where x is the input. So you have a program, and then you have x that is written in your memory initially, and then the program starts running from there. So essentially you check that. So your input is a1 to an, I'm assuming. I'm checking that the first n positions have a1 to an, and all other positions in this tree have a blank. This is all you have to check for whether it is an initial configuration. Okay? Similarly, you can also check whether the last C bit is halting configuration. So this I will hand wave a bit. The other formula is a bit more interesting. So how do I check that two adjacent configurations are actually related by a transition? So when do you think two adjacent configurations are related by a transition? So you see, a transition can only look at that position and either can move right or can move left. So for that particular transition, the current cell and two of its adjacent cells are the only important point. Do you agree with me here? So if you have these three cells, then I can actually compute for you the next configuration. So you just keep rest of the cells similar, and you apply your transition for these three cells and get a new three cells. So for instance, okay, I do not have, so for instance, let's see what is happening here. So here, this guy is taking this B2, changing it to B. He's changing his state from Q to Q dash, and he's going left. Okay? So if you have these three configurations, these three cells, then you can actually compute the next configuration by keeping all these things the same and manipulating only these three memory cells. Do you agree with me here? Yeah, so essentially you just have to check whether there is three cells where the middle cell contains the state, and in the next configuration, the corresponding three cells are according to the transition, and rest of them are the same. This is all you have to check. You just need to write a formula that checks this particular property. So this apparently can be written as a number theory formula. So how do you write it? So you want to check this V is somehow consistent. You are given this C and D. So D is the length of V, and C is these size of the configurations. So what you do is you iterate over all the configurations. So if you remember, this whole thing, all the sequence of configurations is actually our number V. And these are all this C length blocks in that particular number. So you iterate Y over all the positions, and then check whether the every three block components are somehow consistent. If you can a priori compute all the pairs of three blocks that are consistent, for instance, A1, A2, A3 is consistent with A1, A2, A3. Similarly, B1, B2, Q, B3 is consistent with whatever. This should be a small b, small b1, Q dash b, B3, for instance. If you can compute all these three-digit or three PRE numbers that are consistent, then you can actually write down this formula. I'm not going into this particular formula, but it's easy to see. You just iterate over all the cells and check whether this cell is consistent with the cell that you get by multiplying Y with C. So once you multiply this Y with C, you actually enter the next configuration, the corresponding cell, and you can check whether this configuration is same as this configuration. Is this okay? Okay, that is all it is. So yeah, so this match of three is what I hand wave. I do not want to write down the gory details here. So it just checks whether the three consecutive digits in adjacent configurations are consistent, assuming that you have the set of all consistent such pairs. So now, of course, you just put everything together. So you just guess this number, you guess this C and D, check whether C and D are powers of P, and that C is less than D. V is of length D exactly. You check whether V contains the initial part to be the initial configuration, the final C part to be the halting configuration, and then check whether every adjacent configurations are actually consistent. And this psi of m comma x is satisfiable if and only if m has a halting instance. So this in fact gives you a witness for the halting computation. And this not of psi of x is actually true if and only if m does not have an halting computation on x. And hence we have that there is no sound and complete proof system for number theory. So this is roughly the proof of Gödel's incompleteness. Gödel did not prove it this way. This is using, we have the luxury of knowing Turing before knowing Turing to prove this theorem. So these are the three guys three great mathematicians who appeared in our talk. So essentially, what I also want to say is that the sequence of proofs that appeared in history was like this. Cantor proved diagonalization, Gödel proved incompleteness, and then Turing proved the halting problem. Whereas what we saw was not in the same sequence. We saw first Cantor, then we saw Turing's halting problem, and using that we actually saw Gödel's incompleteness. Yeah, so most of whatever I have done is also in this book called Automata and Computability by Dexter Cosen. And yeah, thank you. Yeah, any questions?
Time for questions.
Please. Yes, of course you can generate proofs and prove theorems, but I mean it is not very intuitive. So you get some statement and you can prove some statement, and probably it is either uninteresting or not very intuitive of what is exactly happening. So we are more structured to using structures for proof. I mean, you work with structures directly. Whereas if you take the classical definition of proof, it is just set of axioms and proof rules, and you just prove your theorems using this proof system. But yeah, unfortunately, it is not very intuitive, at least for me. I do not know about others, but it is not intuitive. So we essentially work directly with the structures and try to prove the theorems. Yeah.
Yes, sir.
You are saying that m of x is we can construct theorem xi of m of x if and only if that m also on x in the system.
Yes.
But
Yeah.
there is no program that m halts on x, so that you are saying that at finally m of x belongs to HP inverse.
No. So I am constructing this psi of m of x, which halts, which actually gives you a witnessing computation for this psi of m of x, for the halting computation of m on x. And I am now taking this knot of psi of m of x. So this knot of psi of m of x will only be true if m does not halt on x. Okay, so this corresponds to a member in this HP complement. If you remember this HP complement, the complement of halting problem, this particular formula corresponds to a member in that HP complement. And since we know that the HP complement is a big set, it cannot be even recursively enumerated. We also know that there is no program which actually can enumerate all the theorems of natural numbers. And hence, if there was a proof system, we could also enumerate it. Hence, we also can infer that there is no proof system for it.
So I also have other doubt.
Yeah, please.
We know about Langlois problem. Like we can change anything. Like Ramanujam changed the number to modular forms. We can change anything in number theory to other form. Then if number theory does not have sound and complete proof means, then if we change into other model, like changing a number to modular forms, if we change to that, then we don't have a sound and complete the proof in that system, like in modular forms.
Okay, I don't know much about the modular forms that you are talking about, but actually this statement is very, very powerful. So if you just use Peano's axiom, you already get incompleteness. So if your modular form uses these axioms, these Peano's axioms, if you have number theory as a structure, in which if you have axioms that can describe number theory, you are already dead. So you cannot have a proof system that can prove all the theorems there. So yeah, so I mean, your question is a bit more loaded with definitions which I do not know, so I don't know how to answer it.